The next group of function that we are going to be learning about is called the inverse trigonometric function. Recall that we have trig functions based on the six trigonometric ratios: sine, cosine, tangent, cosecant, secant, cotangent. Now, the names for these functions actually have an interesting history. The earliest recorded study of something that's similar to the ratio of our modern sines is in India, and it used to be called jia, which means the curved part of a bow when you're shooting an arrow, and that was picked up by the Arabic mathematicians, and it was wrongly translated as jib, which means a pocket, which then reached the Greek, and they call the ratio sinus, which is similar to pocket. Um, Anyways, this is how it works: is you input an angle and the output is a ratio, and the ratio relates to the right angle to a right angle triangle which has one of its sides as the angle which is the input. So if you look at the inverse trig function, it's going to take a ratio as input and it's going to spit out an angle. Inverse sine. We use arc sine x equals y. That's defined as a function such that x equals sine of y. Now we have to restrict the value of y between negative pi over 2 and pi over 2. A bonus question here is, why do we need this restriction on y? Hint for this bonus question is that we want arc sine x to be a function. Another notation that you will more commonly see these days is the sine to the negative 1x, called sine inverse x. It's the same as arc sine. I will be using arc instead of inverse just because I think it's a better notation. But recall that the sine inverse x is not actually 1 divided by sine x. Example, arc sine of 1 is pi over 2, meaning if the ratio is 1, then the corresponding angle is pi over 2. Let's look at another example. Tangent of arc sine of 1/3. Now, there's two different ratios involved here, tangent and arc sine. So let's start by letting theta equal arc sine of 1/3. It means sine theta is 1/3, which means that I have a triangle where the angle is theta, and by SOHCAHTOA, opposite over hypotenuse is 1 over 3. So the opposite is 1 and the hypotenuse is 3, and the adjacent is unknown. Using Pythagoras theorem, x squared equals 3 squared minus 1 squared gives me square root of 8, which is 2 square root of 2. But now I go back to what I'm trying to find, which is tan of arc sine 1/3, which is actually tan of theta, which from this triangle is opposite over adjacent, which is 1 over x, which is 1 over 2 square root of 2. Let's continue talking about arc sine. By the general cancellation laws for function and its inverse, f of f inverse x equals f inverse of f of x equals x. So we have sine inverse of sine x is x when x is between negative pi over 2 and pi over 2, and sine of sine inverse x is x for x between negative 1 and 1. Now that we understand how this function works, we're interested in finding the derivative of sine inverse of x. So we let y equal sine inverse x. Sine y equals x, we take the derivative, recalling implicit differentiation on left hand side, which gives us cosine y times dy over dx equals 1, or dy over dx is 1 over cosine y. But remember, since x is sine y, square root of 1 minus x squared is square root of 1 minus sine squared y is square root of cosine squared y equals cosine y, where here I use the identity sine squared plus cosine squared is 1 for all angles. So I get dy over dx equals 1 over square root of 1 minus x squared. Now question for you, can you figure out the graph for arc sine of x? Now recall, we learned how to find the graph of the inverse function if you have the original function f of x. Now you also need to know the derivative of the other remaining inverse functions, and as an exercise you can try deriving those just for practice. Let's look at an example. Given a function arcsine x squared minus 1, you're asked to find the domain of f, the inverse, or sorry, the derivative of f, and the domain of the derivative. Now recall that since the function sine only gives an output between -1 and 1, the function arcsine can only take inputs between -1 and 1. Namely, we need x squared minus 1 to be greater than -1 and less than 1. We solve by adding 1 and taking square root, giving us a domain is between negative square root of 2 and positive square root of 2. Taking the derivative is just a matter of applying chain rule and going through with the calculation. So what you can do is you can pause the video and try to apply chain rule to this particular function, and then your final answer should come out to 2 divided by square root of 2 minus x squared. A domain of this function, you need the square root to be, everything under the square root to be positive, so x squared is less than 2. So it lies between negative root 2, 0 union 0 and root 2. Now let's look at arc cosine x. Arc cosine x is y, x is cosine y. Now in this case, the y is restricted between 0 and pi. Again, concept check, why is the restriction on the value of y? Why is there a restriction? The graph of cosine inverse or arc cosine x looks like that. The range is 0 to pi and the domain is -1 to 1. Now verify that the derivative of arc cosine x is -1 over square root of 1 minus x squared. Now that's something that you can do. And then I'm going to derive the formula for derivative of arctan. By letting arctan x be y, our x is tan y, for y between -pi/2 and pi/2. Taking derivatives, I get 1 equals secant squared y times dy over dx, or dy over dx is 1 over secant squared y. You can use a trig identity, 1 plus tan squared theta is secant squared theta, to get 1 over 1 plus tan squared y, which is 1 over 1 plus x squared. And that's a graph for arctan x. This is because, remember, tan x at pi/2 and -pi/2 goes to infinity and -infinity, respectively. The domain for this inverse function is -infinity to infinity, whereas the range is pi/2 to -pi/2 to pi/2, but not including those values. Let's look at some examples. Evaluate x going to 2 from the positive, arctan of 1 over x minus 2. Since x goes to 2 from the positive, I can rewrite it as x equals 2 plus h, with h going to 0 from the positive side. This makes the limit h go to 0 plus arctan of 1 over 2 plus h minus 2, which becomes arctan of 1 over h. Now, as h approaches 0 from the positive side, it's a very small positive number. It means 1 over h goes to positive infinity, which means that the limit h going to 0 arctan of 1 over h is going to be pi/2, because when the argument for inverse tan function goes to positive infinity, the range, or the result, the output, approaches pi/2. For practice, you can compute the derivative values for arc secant, arc cosecant, and arc cotangent. Here's another example which gives us a kind of application of inverse function and the derivatives. Say you have to prove this identity, arctan x plus arc cotangent x is 1. What you can do is you can let the function f of x be arctan x plus arc cot x. The derivative comes out to be 0. Now if the derivative of a function is 0, identically, meaning for all values of x, that function is a constant, which means f of x equals f of 0 equals f of 1, whatever value you want. Let's say I pick 1. F of 1 is arctan 1 plus arc cotangent 1, which is pi/4 plus pi/4, giving me pi/2 as required. So this is a strategy you can use for finding or proving certain identities at some point. Okay, I'm going to stop this video here, and the next examples are going to be based on integration.